In this video, we're going to talk about polynomial functions and their graphs. And so this is an example of a polynomial. It's just really a sum of monomials. A couple of key things here is the leading coefficient is the number in front of the largest exponent, or the term with the largest exponent. If it's in standard form, it will go in this form where it starts with the biggest exponent and then counts its way down. We call this the degree, the largest exponent. And then the constant term is the term without a variable. It's just constant. It's always the same. It's just the number at the end. So a quick word about their graphs. They're always smooth and continuous. And so you have some examples of polynomials and not polynomials. So if there's any kind of break in the graph, it's not a polynomial. This like cusp or corner, it means it's not a polynomial. But notice how these are smooth all the way through. When you think about graphs in your math experience, it is very likely every graph you looked at, or almost every graph you've looked at, is a graph of a polynomial function. For instance, here are some of the common ones: the line, the parabola, the cubic function, the fourth function, the fifth function. There's some patterns we'll look at. These are all called parent functions, but some patterns we'll look at is what they do at the end of the graph. So on the right and left, what happens. The other thing to notice is notice how this gets a little more flat in the middle at this point of convection as the degree gets higher. Notice the even polynomials follow the same pattern where they kind of look at like a U, and then the odds follow this pattern where they kind of go in opposite directions. Okay, so let's define this a little better. So what happens on the left and right ends of the graph? That's what we talk about with end behavior. So the first thing we're going to do is talk about how to find the end behavior, actually notation, and then we'll do how to find the end behavior as I look ahead. So notation. The notation here, it can be tricky, but we're going to use this notation as x goes to infinity, then f of x, or y, goes to, and then blank. And then as x goes to negative infinity, then f of x, or y, goes to blank. And so this is key because a lot of times people get confused and they'll end up writing this wrong, where we haven't said anything yet, right? We haven't given any kind of answer. This just means as x goes to infinity, or as the graph goes to the right, or on the right side, the y values either go up or down forever. So it's going to be positive or negative infinity here. And this means on the left side, the graph either goes up or down forever. So it's positive or negative infinity. And so let's just go ahead and jump down to these two pictures here. And so as we look at this graph, if I want to discuss the end behavior, I just want to know what happens on the right and what happens on the left. One thing, your reference point should be like starting with the origin. So on the right is this way, and then the left is if you were to walk this way. Well, as you go to the right, the graph falls. So it goes to negative infinity. But before we even fill those in, if we want to discuss end behavior, then x is going to go to infinity. And then we'll use y because we used y up here. Y goes to blank. And then as x goes to negative infinity, y goes to blank. So on the right side, my graph is falling. So that's going to go to negative infinity, And on the left side, my graph is going up. And so that's going to go to positive infinity. Okay, try that for this. Pause the video and even write out the notation. Okay, so here, think about this being your starting point. On the right, the graph is falling. So as x goes to infinity, or on the right, y goes to negative infinity. And as x goes to infinity, or on the left, y also goes to negative infinity. Okay, so that's finding it from the graph. We could also look at this, a polynomial equation, or just the function, and determine the end behavior by using some of the patterns we discussed. So let's go back up here and let's talk a little bit about that. So the first thing we want to do is make sure the polynomial is in standard form. And then Once it is, we look at the leading coefficient. So start with the leading coefficient. And if the leading coefficient is, I'm going to kind of do this sideways to give myself enough room. If it's positive, then it's going to, let's think of the best way to say this. It's going to go, we'll say go to infinity on the right. And if it's negative, it's going to go to negative infinity on the right. So here, if you look just at this, you could say, well, maybe I don't know what the graph looks like, but I know it's going to fall on the right. Or as x goes to infinity, y goes to negative infinity. Same thing here, and then we solidly grasp both that's true. Okay, then after that, we go back to the middle here, and we're going to look at the degree. And if the degree is even, then it's going to do the same on the left. And if the degree is odd, then it's going to do the opposite on left. So in order to do this, you have to know what it's going to do on the right. And you can think about like graphs, like think of a line, x to the first, that's odd. So it goes up on one way and down the other way. Think of a parabola x squared, that's the u. It is going the same direction, whether they're both up or both down. Okay, so let's try this. Let's look at this graph. So this graph had an odd degree. And so it did the opposite on the left as it did on the right. This graph had an even degree, so they were both the same. They were both going down. So for here, like for this one, try to find the end behavior. First, let's rewrite it. So it's in standard form. And then as x goes to infinity, y goes to something. As x goes to negative infinity, y goes to something. And I would always do that first. I would always write out just your notation first, so you can think clearly. Like on the right, it does this. On the left, it does this. So for the right side, you look at the leading coefficient. It's negative, so that means the graph is going to go down. And then this is even, so that means it's going to do the same on the left as it did on the right. So this means this is also negative infinity. This one's a little tricky. You have to really kind of decide, okay, well, what's my leading coefficient and what's my degree? So I'm not going to FOIL everything out. We can just do this by thinking about what would happen. And maybe we'll write out this one step so it's clear. So if we were to multiply this through, then I'd have to do the 2 times the x times the 3x times the 3x. And so that would give me x to the first, x to the second, x to the third. So I have x to the third. And then my leading coefficient, you don't even have to think about the numbers. Just look for negative signs. Like this is positive, 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 positive. So my leading coefficient is going to be positive. And that's a mess, but hopefully you can tell that's positive. And so that's enough for my end behavior. So on the right, I'm going to use p of x because that's what the polynomial is. Excuse me. And on the left, okay, so what happens on the right, this is positive x cubed. And so this is going to be a positive infinity. And then it's an odd degree, which means it's going to do the opposite. So when up here, that means it's going to go down here. Okay, so then it's like, well, why do we talk about end behavior? One of the reasons we talk about end behavior is because it it helps us graph the function or look at the graph of the function. So that's probably what we'll talk about next, is looking at the graph of the function. But reach out if you have any questions.